Okay, Monte, you can go and introduce yourself, and I'll let you tell them who you are and what you do, and we do this information.
Well, welcome everyone. I guess we have somewhat of a full house, and I imagine everyone on is preparing for their upcoming certification exams. So best of luck to you, and hopefully this is helpful. About myself, I'm Monte. I'm the Chief Operating Officer for Silicon Valley Clean Water, which is located in San Mateo Bay, or San Francisco Bay, just south of San Francisco. We treat all the wastewater from Menlo Park, San Carlos, Redwood City, Belmont. So we treat about 14 MGD. We're designed for 29, and it's very challenging as we have an average daily flow of about 14 MGD, but with 2 inches of rain, we can go to 80 MGD within 2 hours. So we're always looking for good certified operators to bring in to help us and to train, as we're all faced as we manage wastewater treatment plants with the onslaught of retirements that are happening right now. And there's a lot of openings and a lot of demand for certified operators. So I'm really glad you're on today, and I wish you the best in your tests. Getting right into it, activated sludge, it's fascinating. I mean, things with activated sludge is it consists of living organisms that do the bulk of the work. Move that suspended dissolved portion of starches and sugars that are in the wastewater. You know, it's very easy to remove the heavy solids with screening, or you can settle them out, or the stuff that floats. It's easy to take that off in your primary clarifiers as scum and fats, oils, and greases. But what's really hard to treat is that colloidal stuff that doesn't want to sink, doesn't want to settle, it doesn't want to float. How do you get rid of that? Well, that's when you have to have biological processes to do that. The activated part of the word activated sludge refers to it's teeming with microorganisms. It's alive. It's bacteria, it's fungi, it's protozoa, it's a lot of different microbes, which we'll talk a little bit coming up. And the activated sludge process is a biological process that uses microorganisms it says here to speed up the decomposition of waste, but it really is to assimilate the colloidal stuff that's in the wastewater. And basically, I always refer to that as your BOD or your sugars and starches. This chart is probably one of the more important ones, and one it basically is a really nice, yeah.
Your sound is going in and out a little bit. I don't know if there's anything you can do on your end, but just to let you know.
Maybe, alrighty. Is that any better, Robert?
I'm not sure. Let's try and let's see if that helps.
Okay. One of the things with this chart is it's a very good indicator. If you do microscopic exams of your activated sludge and you can actually see the microbes that are in there, it gives you a good indication of how your process is doing, how it's settling, how it should settle. And also, when we'll talk more about these parameters that are down below, your sludge volume index or your SVI, your food to microorganism ratio, which is your FDM, and your MCRT, which is your mean cell residence time, and how that affects your settling and what microbes should be present in your microscopic slides. Good microorganisms that you want to see in your activated sludge, stock ciliates are really the best indicator. If you create that environment in your activated sludge where you have a really good, you're in the right zone. So you're going to see some rotifers, you're going to see ciliates. Then getting back to here, when you get into your sludge ages, you'll start to see, as it gets older, you'll start to see, more complex microorganisms. You'll start to see nematode or rotifers, stock ciliates, free swimmers. But when you start seeing nematodes pop up and basically worms, your sludge is pretty old. It's most likely outside of the range that you're really looking for. And then if you don't see any stock ciliates and some of these other microorganisms that you're hoping to see, then you might be really on the young side. So again, it's important to do microscopic evaluations where you take a sample of your activated sludge and you look at it through a microscope. It'll tell you a lot. One of the things I hope you don't see in your microscopic slide are the filamentous bacteria. These will cause you a lot of problems. They'll cause problems with foaming, with settling issues, turbidity issues, just not great microorganisms. Generally, these are low DO environments. Dissolved oxygen levels in an activated sludge, really high inventories, a lot of microorganisms. You'll start to see these bad, we call them bad microorganisms or bad bugs, starting to be present in your activated sludge. And it should be a really good indicator that you need to look at your process and you're most likely going to need to make some changes. To keep your activated sludge nice and healthy, you need food in the form of BOD, sugars and starches, that the microorganisms can readily. You want a good supply of oxygen, and you want really good mixing to keep the microorganisms and the oxygen and the food in a homogeneous solution so the microorganisms have readily access all the food and air that they're going to need. Organisms are a big portion of them. And that's where most of the work in that aeration tank. So your microorganisms are assimilating the sugars and starches there. And then once it passes through, it goes into a secondary clarifier. The purpose of a secondary clarifier is to settle out your microorganisms. Basically, you want them to settle to the bottom where you can capture them and return them through the return activated sludge or RAS back to the head of your aeration basin. And off of that return activated sludge line, because they're nice and concentrated, you can actually waste what we call waste activated sludge or WAS. You can pull some of the microorganisms out of your system and send them off to another process. And that's how you maintain your inventory. And your secondary clarifier works kind of like a bucket and a hose. You're putting flow into that bucket and it's a continuous flow. What's that bucket going to do? It's going to overflow. Well, hopefully it's going to overflow. You're putting it in a rate where the clean water is going to overflow and go into the next process. So this is kind of a simplified version of a conventional process. There's many other variations of this, but this is the one you'll see the most common. Two different terms used in activated sludge. There's the MLSS, or your mixed liquor suspended solids. And that's the concentration of suspended solids in your aeration tank. Another term called mixed liquor volatile suspended solids, and that's the MLVSS. And that's a concentration of organic or volatile matter, which really is a direct relationship to your mind. The way that they differentiate these two is in the laboratory. They'll take a sample of your activated sludge, they'll dry it, and they'll weigh it to basically get, it's a total suspended solids test. So you can see how much solids you have in that particular sample, and you can correlate that to your activated sludge system. But that's all of the solids that are in there. Remember, you've got inorganic solids in there too, things like grit and sand and colloidal things that aren't microorganisms and they're not alive. So what they do is they take that mixed liquor suspended solid sample. Once it's dried, they get that concentration. They stick it into what they call a muffle furnace at 550 degrees C, and they burn off all of the organic matter. Everything that's organic in there, which includes all your microorganisms, burn off, and all you're left is the inorganic stuff. So basically, that's a correlation and a way you can get a really good idea of the actual concentration of microorganisms that you have in your activated sludge is your MLVSS. And as we move forward through these slides and get more into the process, you'll see how important that is. One of the things that we look at very often daily is your food to microorganism ratio. And it's how much food do we have coming in and how much, what's the concentration of microorganisms we have that's going to eat that and utilize that food. You don't want to add too much food because it'll just pass through if your microorganisms can't eat it all. And then if you put in too little food, we'll talk a little bit more about that, you'll end up in other process issues. So here's the calculation for the food to microorganism ratio. And we'll actually calculate one of these later on at the end of the slide, and we'll show you the correlation. But you'll see that the food to microorganism, because it's looking at microorganisms specifically, it uses the MLVSS number. And sometimes the MLVSS, or the volatile suspended solids, will be reported out as a percentage. And some treatment plants will say, hey, my MLSS, was 2,000, and my MLVSS is 80% of that, or 60% of that. So that means 60 to 80%, or whatever your number is. Ours usually runs around 80%, is microorganisms. So we only have about 20% of that inorganic sand and grit and those kind of things in our activated sludge. There's a term that they use called sludge age, and it's a length of time, 1 pound of solids is kept under. It's important to know this, and it's used just as an indicator, just to know, hey, am I feeding the right amount? How much food do I got going in? And do I have my suspended solids inventory correct? We personally don't use sludge age. It's something, there are some plants that actually, especially older plants, that actually still use this as one of their parameters in process control. But we tend to use other indicators, which sludge age is a good indicator because it'll kind of tell you your loading of how much food you can load, how much and a high rate where you're going to add the highest loading of food to microorganisms are really high is 0.5 to 2 days. Conventional is 3.5 to 7. That's for most true. Extended aeration is where you have, if you have the luxury of having a lot of property, you can have giant aeration basins and really reduce the amount of food and add a lot of food to it. But on the other side, you have a lot of inventory to manage too, and a lot of microorganisms. These are two very important things that we use for process control. At Silicon Valley Clean Water, we actually use the mean cell rate. Is the average time in days that a microorganism stays in our solid retention time, which is kind of important. And it's the first time in the new SAC state manual in the 8th edition. It's the first time they've ever differentiated between the two. A lot of people use these interchangeably, but they're really not. They are different. Mean cell residence time is looking specifically at a microorganism, how long it stays in your system. Solids retention time, or the SRT, is the total amount of solids. How long does that stay in your system? The MCRT uses the MLVSS concentration because it's directly related to your microorganisms. And the solids retention time uses your MLSS. Let me tell you a real quick story. We were using our solids retention time at a plant I ran here in Atwater, California for many years. And we were looking at our SRT and our MLSS. Our MLSS, we couldn't waste enough. It just kept growing. It just kept getting larger, and the numbers kept going up and up and up. And it's like, oh my gosh, what's going on? We're not wasting enough. We got behind. So we were wasting like crazy. We were getting as much stuff out of the system as we could, trying to bring that number back down. Then we started noticing, it's like, wait a minute, our settling doesn't look good. Our turbidity, the water's cloudy. We're starting to see BOD in our effluent. So that means it's passing through. What is going on? What's happening was I was looking at the MLSS number and the SRT, and the city guys out in the collection system hired a contractor to clean lines. Well, guess what? Out here in the valley where we are, it's all sandy soils. They put a bunch of sand, sugar sand, that doesn't like to settle, it stays colloidal, into our system. By using the MLSS number, we were sitting there trying to waste sand out of our system, and we ended up wasting too much of our microorganisms out. And we got in trouble. We almost violated. But if we would have used the MCRT and just kept to the organic part, we would have known that. We would have seen that difference, and we wouldn't have over-wasted and wasted out our microorganisms that were doing all of our work. So that's one of the important differentiators for me personally of why I like to use the MCRT versus the SRT. The common laboratory procedures that operators do is a 30-minute settleometer. And I like the operators to do this because they can actually see this is a simulation of what the secondary clarifiers are doing. Once your activated sludge goes into your secondary clarifiers, what's happening? Well, you can see on good settling, and unfortunately it's kind of a crummy picture. The settleometer jug there is kind of scuffed up, so it looks kind of cloudy, but actually that's very clear water. And this is when you see a nice, dense, compact sludge settling and clean water up above. The next over, which is the medium settling, you see a lot of pin flock. You see it's kind of cloudy up on top. That's not a good indicator of good settling. And when you get pin flock, generally you're in the older age sludges. It's settling too fast. And when it settles too rapidly, you'll end up with this pin flock that'll cause turbidity. And if you have a filtration process, all that pin flock's going into your filters for your tertiary and it's plugging your filters up, causing your run times to reduce. It's just not a great situation to be in. And then if your sludge is sitting too long in your secondary clarifiers and you have very low DO, you can actually see it split. And what that is denitrification. The bacteria in there, the DOs get so low, the bacteria are using what they call nitrate, NO3, as their oxygen source. And when they pull all the oxygen off that NO3 molecule, it releases nitrogen gas, and you end up floating sludge in your secondary clarifiers, which is also a problem. So you don't want to get into that situation either. That's why I like my operators to a good snapshot of what's happening. One of the other things you'll see on certification exams, and this is very important to operators and design engineers, and it's an indicator of how well your solids are going to settle. So an SPI, so your sludge volume index below 150 ratio, and it actually indicates good settling. What design engineers, let's say you're going to expand your treatment plant, and they go, well, how many new clarifiers are you going to need? What's your current SVI look like? How is the sludge characteristics that you have now in your activated sludge? How does it react? How does it settle? If it's poor settling, you may need bigger clarifiers. If it's good settling solids, you'll need smaller clarifiers and could save, a significant amount of money by being able to do that. But again, this is another indicator, and you will see this on your certification exams too. So it's very important. And this also uses that, it's interesting that it uses the MLSS and the MLVSS. So one of the things that earlier was your RAS, your return activated sludge, and your WAS, your return activated sludge is what your return your clarifiers, and the WAS is what your. So one of the things is like, well, how do you calculate how much WAS you should take out of the system, maintain your inventory? Well, if you have a target in your MCRT, and we try to keep around 2 days, very, very low MCRT, we can actually take the MCRT equation, manipulate it using algebra, and we can get the WAS on one side, and we can plug in all of our information that we have for our process data that day. And we can actually say, I want an MCRT at 2 days. I need to waste this amount of inventory out of my plant. So I just wanted to let you know that the MCRT equation or the SRT equation is very important, and you can manipulate it to use it to help with other process parameters. Your activated sludge too, it's interesting concept you keep in mind, and I've actually seen this on certification exams in the past. There's two different ways that your microorganisms find their food to basically take it out of the water and be able to begin to assimilate it, utilize it. One is called the adsorption. And adsorption, basically it's the food, the suspended food that's in there that's actually going to stick to the outer side of the bacteria or the microorganism. Basically, it just sticks to the outside. And then as it sticks to the outside, then it can either be assimilated through the cell wall by the bacteria or microorganism, at a kind of a controlled rate. Absorption is where it actually takes it inside the body of the microorganism and it utilizes the food. Some of your higher forms of microorganisms like rotifers, well, actually you'll see them ingest it. They'll actually eat the solids and you'll see it go through. And some of them, if you get larger ones and you have a really high resolution microscope, you can actually watch it pass through their whole system. So there's two different ways. One is adsorption, where it sticks to the outside of the microorganism and it can start to bring it through its cell wall. And then there's absorption, where it actually kind of ingests it and actually brings it into their cells that way. Oxidation is another interesting phenomenon that has to happen in activated sludge. We have to add oxygen. It's an aerobic process. And I've looked through many biology books, chemistry books. When you look at the chemistry books, this is very complex thing that happens, oxidation. And I found this in one of my old textbooks when I was in college, and they kind of pared it down into very easy to understand. And I've kept this with me all along. Basically, there's two forms. One, there's oxidation, and then there's reduction. And you'll hear redox reactions. You'll hear about oxidation, reduction, and chemical equations and chemical reactions. But in activated sludge, the important thing is oxidation is a gain of oxygen. You're gaining oxygen into the microorganism, into the food. That's why you have to add oxygen, because you're utilizing it. Reduction, on the other hand, you're losing oxygen through a chemical reaction, and it's actually kind of giving off oxygen. So that's the two biggest things. And just remembering that oxidation is a gain of oxygen and reduction is the loss of oxygen, that will be enough to get you through most of your certification questions, especially in the multiple choice and true and false. Another test that we run in operations called an oxygen uptake rate. We'll take a sample of activated sludge. We'll put it in a BOD bottle because we can seal it off nice and tight so you can the outside air oxygen into the DO meter inside that BOD bottle. And the operator will turn on the DO probe, which has a mixer on it, and then they will log the DOs, the dissolved oxygen concentrations in that sample over every minute for 15 minutes. And some take it out a little further to 30 minutes. But it's interesting because you'll see that the oxygen's used up usually pretty quickly within the first half of that time period. In the first 5 to 10 minutes, most of the oxygen's utilized. And then after that, what happens is most of the food in that sample has been used up. So the bacteria aren't expending much energy to utilize the food. Therefore, they're not uptaking more oxygen. So it's a good indicator of, is my F to M correct? Also, it's a good indicator to see if you have anything else in your activated sludge system other than biological activity going on. And what I'm talking about there is toxics. You can get some toxic chemicals dumped on us in a wastewater treatment plant that you don't know is coming down the pipe. And some of them are oxygen scavengers, and you'll see your oxygen levels drop dramatically. If you see some weird things happening in your settleometer, if you see that you got poor settling in your secondary clarifiers, an OUR test is a really good, quick check to see what's happening in there and to see if you are getting hit with a toxic load. Another thing we talked a little bit about, if your F-dem ratio is very low and you have low food concentrations, the microorganisms can enter what they call endogenous. That's basically when they're starting to kind of, you don't want to get into this situation. You'll see that people or wastewater treatment plants that have large industrial dischargers coming to them that usually have a high BOD load, say a food processor. Well, the food processor cleans out their tanks once a day. You get this giant shock load of food coming into your aeration basin, and it's like, wow, my DOs dropped to nothing. I got more food than I have microorganisms. So then as an operator, you try to compensate for that. Say, well, I need to get more bugs in here. I need more microorganisms. Well, then what happens when they quit washing their tanks and that shock load had passed through? You can end up in endogenous respiration, which is not a good situation to be in either. One of the things that we try to do with our industrial pretreatment program is our industrial pretreatment inspectors are aware of this kind of thing, and they require the industries to put in large holding tanks, and then they pump and meter the flow to us to where our activated sludge system is kind of getting a constant, not this big shock load. They're getting this constant flow of food in from that industry. So those are things that your industrial inspectors can really help you out with. But it's this also I've seen on many certification exams. They'll talk a little bit about endogenous respiration and what is it. And usually it's in multiple choice questions. I'm going to go through this kind of quickly. One of the things to have a good, healthy activated sludge is you need aeration, you need oxygen. How do you get that into your activated sludge system? Well, you can do it mechanically. They have mechanical mixers that will actually cause a lot of splash atmospheric oxygen and bringing it into the tank. Diffused air, where you have actually taking air, compressing it high pressure, blowing it through these diffusers. And what the diffusers do is they break up the bubbles, which actually create more surface area and actually creates more opportunity for your bacteria and your microorganisms to get that. It's one big giant bubble, doesn't have a lot of surface area. If you have a whole bunch of little tiny bubbles, it's much better, and you'll get much better oxygen transfer into your microbes. Then there's also a hybrid. There's a mechanical aeration and diffused air. And actually we have invent mixers, which actually mix the tank, and we have a diffuser air. And as the mixer goes, it's taking the air and it's dispersing it throughout the tank.
Excuse me, Monte. We still having a lot of problems with the sound. I don't know if there's anything you can do on your end at this point, but I just want to let you know.
Okay. Thank you, Bobby. Maybe I can lean in closer to the microphone there.
All right.
But sometimes they'll have a combination where you'll have a mixer and you'll have a diffused air system to where you're getting those fine bubbles. And then the mixers, if it's a large tank, it'll just disperse those fine bubbles out there to where you can get better oxygen transfer. Then there's the blowers for diffused air systems. And there's different types of blowers. A very popular one is a positive displacement blower, where it'll actually trap air in these little compartments, and as it spins around, it'll release it. And as it releases it, the air can't travel backward, just bringing in the next pocket of air, next one, and the next one. It'll actually create very, very high pressures. Very, very, I can put it simply, they're not overly efficient energy-wise, but they're very reliable and robust. The popular one that you'll see is centrifugal blowers. And again, these are usually on larger systems that need a lot of air, and they can transfer a lot of air into. But again, big motors, not the most efficient. What we're starting to see more of are the turbine blowers. The turbine blowers take a lot less energy, much more efficient, can provide that high pressure air that you need, and a lot of it. We just went to new Spencer micro turbines, and we saw a sizable decrease in usage. And also we got a very large rebate check from our energy provider, Pacific Gas and Electric, putting in this energy efficient blower system. But we're really happy with it. The other part is the micro turbines are a lot less noisy than the centrifugal blowers or the PD blowers. Three things that operators really have to concentrate on in your process control is what you have coming into the plant and your influent. Basically your primary effluent, what's coming into the aeration basin, and your BOD. Hopefully there's no toxics in there. the environment for treating your waste. What is the condition of your activated sludge process? How healthy is it? Remember those health things you need to keep it nice and healthy. And that what leaves the plant in the effluent, which can tell you a lot of how effectively your activated sludge system's working. I put this table in, and it's a really good table to look at, and some of it kind of commit to memory because this will help you a lot on the certification exams. But just to know you're in the right ranges to keep your activated sludge system nice and healthy, and also that your activated sludge system size properly. You know, COD is your chemical oxygen demand, and it includes your BOD. It's chemicals in there that can oxidize. Also, it's your biological activity. The BOD is just a measure of your biological or biochemical oxygen demand. And basically, it's what we mainly use in wastewater. The difference is a COD test takes about 2 hours, and you can get it really quick, results really quickly if something's going on. And a BOD test takes 5 days to get the results. And then your suspended solids, what your DO ranges should be, typically chlorine residuals. You don't want any chlorine in your activated sludge if you can help it. And then your clarity, turbidity, and the other indicator is very important. Make sure that your pH is in the right ranges because you will have permit requirements for pH. And also you want to keep your pH as neutral as possible for your activated sludge to be nice and healthy. We use a process control management plan, referred to as our PCMP. It's driven by a program called HOCWIMS. That's provided by HOC, and it can interface with our SCADA system and Wonderware. It interfaces with our laboratory and their LIMS system. All that data is put up, and then HOCWIMS can actually go get the data automatically. So our operator, it takes out operator error for input, and then it does the calculations for us, and we can print up these flash reports at any time and look to see what's happening. And our guys will set what we call control limits. There's lower control limits, warning limits, and then in the green, you can see what our targets are. For instance, our MCRT target is 2 days. Well, guess what? If you look at our average, we're at 1.3. We're beyond the lower control limits. So we need to basically back off on our wasting and get more inventory in there to correct that. So we look at these things daily. We have process control meetings every week where all the operators get involved. They look at these things, and it's very, very important to have this information available to your operators so they can look to see what the health and condition of your activated sludge is. There's some abnormal conditions as operators you need to watch out for. Rising sludge or bulking. It's usually low DO concentrations in your secondary clarifiers, and also your solids can go septic in your there too long, and you can start or you're not removing the RAS fast enough. It causes a lot of issues, and you can see there's a lot of suspended solids leaving that secondary clarifier going into your next process. So that's a big problem. Toxic loads. Again, we get dumped on all the time. We try not to, but we can't control everything. And some of the toxic materials can actually wipe our activated sludge system. Very careful. And again, it's very important to have a good industrial pre-treatment program. Foaming and frothing. These pictures are a little extreme, but I kind of put them on there because they are so extreme. Hopefully none of us ever see foaming like this in our activated sludge systems. I've seen it once, similar to the picture on the left. I walked into a treatment plant when I was working for, and I just didn't believe my eyes. And it was something that just had happened, and I actually spent a couple of extra days there helping them get that back under control. The foaming or the frothing on the other side was actually someone dumped soap on the treatment plant. That's why it's so white and billowy. And they had a big load of detergent come in, and that's what happens when you put detergent in an activated sludge with really aggressive mechanical aerator. So again, watch your process, watch your microscopic slides for any nocardia that starts to show up or filamentous bacteria, because your plant, could end up looking like that picture on the left. So again, these are abnormal conditions, but these are things you really need to be aware of. And if you see this, it's a serious problem. And, our favorite thing that we love on all wastewater certification exams is the math. I'm sure everybody loves the math sections, being facetious. But I just want to throw up a real simple food to microorganism example where we're looking at the amount of food we have coming into our activated sludge system, and do we have the right inventory of bacteria for that amount of food coming in? The known, we know that the flow coming in is 10 mgd. The BOD, it's 120 milligrams per liter. The aeration basin volume is 1 million gallons. The mixed liquor volatile suspended solids is 1,500. And then I just threw the pounds formula because that's the main formula you'll be using throughout this example. So when you do the calculation and start plugging the numbers in, you'll notice that we have a food to microorganism ratio of 0.8. What does that mean, 0.8? Well, remember that's a ratio. You have to go look at your process control plan. I go back to ours and look, okay, what does our F to M, which is number 4350, our F to M target is 0.7. So we're actually into our upper warning limit. It means we have more food coming in than we have microorganisms. But that also kind of tells us that, wow, our MCRT is low. It should be higher, which means we need more microorganisms. So all of these indicators are telling us we're wasting too much. We need more microorganisms. We have more food coming in than we can handle. And so we need to back off on the wasting. And if I had the next report on this, you would see we did back off on the wasting, and all of those red flags all went away. But again, it's a really good quick indicator. And it's always good to go back and see how these numbers actually play into your process. What they need. And I wish you the best of luck on your exams. Again, we need more good certified operators. I'm not sure where everybody's from, but I know BAYWORK's reaching out, especially with this online training, and we're getting people from Central Valley, from down, I think I even heard up Sacramento way. We're getting them up through Santa Rosa. So it's reaching out to a very large area, and I'm really happy to be part of this. If you have any questions, I think Robert's handling the
Yeah, I'm here, Monte. Thanks so much for presenting and everything. This is great information. We'll take some questions now or comments from you. And you may have more questions because some of the sound was going in and out, but we can do some of those now. You can just sound out, unmute yourself, or you can type it into the chat either way.
I did want to make one correction. I have a mistake here on one of the slides, and it's on the where it says MLSS times MLVSS. That's not correct. You're going to use one or the other.
Say again, Monte. I can't hear you, Monte.
Happened there. You're going to use one or the other in this example. For your sludge volume index, if you have to do a calculation.
Go over that again, Monte. You kind of broke up, so that makes sense. I hears you.
Yeah, there's a mistake in this slide on the equation. It says MLSS times your MLVSS, and that's not correct. You're going to use one or the other. whichever one you choose to use. You're going to use the MLSS or you're going to use the MLVSS.
Oh, I see. It should be or in the denominator.
Yeah, in the denominator.
Okay.
The typo on my part.
All right.
I just wanted to make that clarification.
Hopefully everyone caught that.
Yeah.
All right. Great catch. Any questions? Again, you can type it in the chat or just unmute yourself and ask it.
I was away from my screen for a few seconds. Could you go back to showing where the typo was, just so I can take a screenshot and have it for later?
Certainly.
Yeah, the denominator there, it should be the MLSS or the MLVSS, not the two multiplied times each other.
Okay, got it. Thank you so much, Monte. I really appreciate your time today.
Yeah, well, I feel honored to, to do this for you guys. I went through and plucked out the stuff that I can remember on certification exams and, teaching classes for the Bay Area Consortium for Water Wastewater Education, BACWWE. And these are the things that the students would come back after their certification exam to go, wow, I had a question on this, I had a question on that. So this is from my memory, trying to take a full semester class and pare it down into 45 minutes. So hopefully I gave you what you guys will need to make it through and pass your exams.
There's a question here, Monte, about slide 8. Is that the influent? Is it just basic, or does it represent the primary?
Primary influent.
Okay.
Basically, the way that this is a snapshot out of one of the SAC state manuals, and it's basically, it's the influent going into your activated sludge process, aeration tank. So that would be primary.
You went in and out, Monty. We can't hear you right now.
Did I? Gee, many Christmas. I'm gonna have to work on my microphone.
Yeah.
I really sorry about that.
That's
It's
okay.
primary effluent, influent.
Okay. All right.
And now with the online certification exams, which I don't know anyone that's taken one yet, and I haven't taken one. I'm not sure. I mean, we always used to get credit just for drawing a picture in a math problem or a word problem, but I don't know how that applies now because everything is online. So
Okay.
it's good to look at these pictures and kind of commit them to memory to be able to answer the questions.
Okay, Monty, want to get some clarification on on this slide here. Is this effluent or influent? Primary effluent or primary influent?
It's primary effluent that is your influent going into your activated sludge system. So the influent, where influent is right there, it is primary effluent. So it's flowing out of your primary clarifiers into your aeration basin.
All right. Someone else says, I thought it was PE, not PI.
It's PE. It's primary effluent.
All right. Okay, looks like that cleared it up.
Yeah, thanks for bringing that up because I'm going to change this slide because that is confusing. It's referring to the influent going into the activated sludge system, but it's generally primary effluent.
Yeah. Yeah, someone said they see it now, but yeah, you might want to make a little adjustment there, some kind of indication. Yeah,
Yeah, I absolutely will.
wonderful. Well, wonderful, everyone. We thank you so much for staying with us today and attending. And we thank Monte. Monte, you always come through when we ask, and we so appreciate you and appreciate partnering together. And certainly we'll be doing more of these. So stay tuned, and stay tuned for other BAYWORK events, and stay tuned for other BAYWORK events. And stay safe out there. And we appreciate all the great work that you're doing.